Hey folks, in this video we're going to be talking about the basics of solution, kind of like a pumpkin spice latte, maybe not. There's not even pumpkin in those anyway, it's butternut squash. Anywho, I want you to be able to describe aqueous solutions using particle theory. I want you to also be able to describe the process of dissolution, using particle theory. And that's cool because if you're going to have a solution, you need to have dissolution occurring in order for it to be made. And I want you to be able to explain why solutions are useful in chemistry using particle theory, because I'm all about that particle theory. Let's get cracking. Solutions viewed through particle theory. Well, we have to know that a solution is going to have a solvent and a solute, and when we draw them using particle theory, we're going to identify them with unique looking particles. So let's use for an example a solution of sugar and water. Water would be our solvent here, and we're mostly going to talk about solutions with water as a solvent. We're going to focus on aqueous solutions, and those are ones that have water as a solvent. Aqua, water, wonderful. Sugar is going to be our solute, the thing that gets dissolved into the solvent. Let's look at a pretty picture of this. All right, it's not that pretty, but it does the job. We can see we have water particles, and they're surrounding, for the most part, our sugar particles, and they look different. We can represent a solution in this way using particle theory. Neat, neat. Well, these solvent particles here outnumber the solute particles, and that's typically going to be the situation. It's kind of hard to dissolve somebody if there's more of it than you. You need to be able to surround that stuff, as we'll see a little bit more later. Solubility is a term that we're going to use when we talk about solutions. Solubility refers to whether or not a solute can dissolve into a solvent. So if you, for instance, try to dissolve wax into water, you might find it quite difficult. You might find that it doesn't dissolve. Whereas if you try to dissolve sugar, you might find, yes, this dissolves very well, particularly if I agitate and stir it. If a chemical can dissolve, we're going to call it soluble. If it can't dissolve, we're going to call it insoluble. So wax and water, that wax would be insoluble in water, where sugar is going to be nice and soluble in water. Solubility is also going to affect how much solute can be dissolved. So, for instance, if you take some salt and you pour it into some water and you stir that puppy up, well, your salt will eventually dissolve. But if you keep adding and keep adding and keep adding lots and lots of salt, it's eventually going to stop dissolving. And that's because the water can only hold so much salt. Imagine if I kept adding sugar particles up into here, eventually it would be preposterous that you would have a liquid there totally. It would be mostly just solid sugar. And so a solution can't hold, when it can't hold any more solute, we refer to it as saturated. A saturated solution is one that can no longer take on holding more solute. Well, let's talk a little bit about water, ions, and charge, because it's important for us to understand these things when we talk about solubility and solutions. Ions have charge. Hopefully that's something that you're very comfortable with. An ion is something that has charge. And so these charges we're going to represent by whole numbers. For instance, sodium has a +1 charge. It's not like 1.5 or 1.222. It's +1, baby, +1. And oxygen, the oxide ion, has a -2 charge. It's a whole -2. It's not 1.95567 rounded up. We're going to call it -2. The whole ion itself is charged as well. If you have an ion of sodium, that +1 charge is spread throughout the whole gosh darn thing. Well, this is different from water because the atoms in water have what we call partial charges. And a partial charge is like a fraction of a whole charge. It's not 1 or 2. It's actually going to be less than 1. And these partial charges are interesting because unlike the charges of an ion, they're located only on specific atoms in the water molecule. What? And these partial charges in the water molecule balance out because water, as we know, or hopefully know, is an overall neutral molecule. We don't talk about water as being an ion. It's a neutrally charged molecule. And molecules typically have neutral charges. So these partial charges on water balance out. And the partial charges, instead of just using a plus sign or a minus sign for these dudes, we're always going to use a Greek symbol delta. It's a lowercase delta. And we're going to use that with a plus or minus to indicate whether or not there's a partial positive or a partial negative. Let's take a look at that. For instance, but let's look at that sodium too. If I wanted to represent sodium, I'd use probably just a ball because sodium is a single ion. And I'd give it a plus symbol. Say, hey, it's sodium plus. For my oxygen, I'd put a 2- in there to be like, hey, it's got a -2 charge. But we just did oxygen. But for water, I would put a delta- on this oxygen because the oxygen in water carries a partial negative, and each hydrogen carries a partial positive charge. Neat stuff. Well, these partial charges can interact with ions and other partial charges. And that's pretty dope. That's what lets water do some of the wicked cool stuff that it can do. So the hydrogen ions, atoms in water can interact with negative charged anions. So these dudes could potentially interact. There would be some attraction between them because, as we know, opposites attract. And on the opposite side, we've got our oxygen with a partial negative. Well, this dude and sodium could happily interact, as well as this dude and other cations. This partial negative is going to be attracted to positive charges because opposites attract. Yeah, and so this allows water to be real dope at dissolving many ionic compounds. Let's look at that. So let's imagine we got some sodium chloride, NaCl, and some water. Here it's a solid. It's in a real cool lattice. We saw lattices in our last video on ions. Nice. And here's some water, represented in particle theory mode. Well, if we add them together, the sodium chloride is going to break apart. The sodiums and the chlorines are actually going to separate out. They're going to become ions. Separate ions doing their own gosh darn thing, and they're spread out by the water. And so we can actually represent this with a little bit of a better picture that I stole from them interwebs. Here we can see that sodium chloride. We got the pluses for our sodium, the minuses for our chlorine, and here are waters. And the actual solution, we can see the sodium and chlorine ions are going to be separated, and they're going to be each held onto by these water molecules. Let's take another look at that with these partial charges in an image that I created. So here we can imagine we've got just a little bit chunk of a sodium chloride crystal, and we have our waters. Their partial negative charges are going to interact with these positive charges, and they're going to be able to pull this dude away. And as they pull it away, more water molecules are going to come in and start interacting with the other sides of this positive sodium ion. And as these dudes start to come in, oh my gosh, there's going to be an interaction between these dudes, these chlorines, and these partially charged hydrogens. Well, as this sodium gets pulled away, we can imagine water is going to swarm around it because all these partial negative charges like to hang out with this dude. And as water swarms in around this, we've got more hydrogens that are going to point back towards our original source of the ion. And now these partially charged hydrogens are all going to be like, yo, what up, chlorine? I see you got a negative charge there, boo. And they are going to be able to start pulling these chlorine ions off. And we can imagine this process just continuing. As more and more water molecules are going to sweep into this gap, they're going to help pull off these remaining sodium ions, and the process will continue. And here's some more of those bootleg images I stole. I guess they're not bootleg, but I just stole them. Here's their pretty version of showing what I just showed in this picture. We can see that from our original solid, we have many water molecules that are doing the job of pulling apart the structure until it is completely pulled apart, and the individual ions are now no longer together forming a lattice, but they are dispersed throughout the solution. Neat stuff! Cool. Well, let's also talk about sugar and water again, because sugar is kind of nifty. It does dissolve, but sugar is not an ionic compound. Here's a better picture of that. Sugar we can kind of represent by these hexagons, and the reason sugar is able to be dissolved by water, even though it's not an ion, is because sugar also has partial charges. What? So the partial charges on water and the partial charges on sugar work together to allow dissolution. Well, why are solutions useful for chemistry? Let's talk about that as our last concept. In order for atoms or molecules to react together, they have to touch. They got to smack into each other. These particles, they got to bump. And it turns out that solutions allow for better mixing up of these particles than solids. Let's take a look at that with some example. Just a generic dude. A plus B gives us C. Imagine we got A and we got B. We got to make those dudes touch. They are solids though. So we're going to just eventually, I mean, this could be a very tiny piece of stuff if it's just made of that many atoms. But these particles are going to, these larger particles made up of many small ones are going to have to interact. And the only way they can really interact is just by like mashing into each other. In which case, all these dudes don't really interact. It's only the pieces on the surface that will interact. So we get a reaction occurring on the surface, making this new dude C. But the rest of the molecules, or the rest of the particles, don't interact. They can't react because they don't interact. But if we got a dope solution, if these dudes are aqueous, dissolved in water, then imagine A dissolved in water. We got B dissolved in water. If I mix those two things together, A and B are now going to swim all around up in the water. The individual particles are now going to have a lot more opportunities to interact with each other. Look at all this. Look at all this interaction I've shown in here. And now there's many more opportunities for the reaction to occur because there's just a lot more interaction between the particles. Anywho, that's the end of this video. I hope you understand a little bit about solutions and how particle theory is really helpful for viewing those solutions. Solutions are everywhere in your life. Yeah, solutions. Ta-ta. Have a great rest of your life.